Welcome to Fuzzy Mathematics, the basics. In the previous lecture, we have talked about the classical extension principle and fuzzy extension principle. Using the classical extension principle, we can extend a function f from x to y to the true set-valued function. In this lecture, we are going to talk about the properties of these true set-valued functions, which will be quite useful in the next lecture. First, theorem 1. Let f be a function from x to y. Suppose A is a subset of x. Then the image of A is the empty set, if and only if A is the empty set. And the preimage of the empty set is the empty set. But the preimage of a set is the empty set does not imply that it is the empty set. I will explain what I mean by an example. Let's take a look at example 1. Given a function f of x equals x squared. The domain of f is the set of real numbers R, and the range of f is the set of non-negative real numbers. Suppose B is the set of negative real numbers. Then the preimage of B is the empty set. But B is not the empty set. That means the preimage of a set is the empty set does not imply that it is the empty set. But if the function f is surjective, then the preimage of a set is the empty set, implies that it is the empty set. Next, theorem 2. Let f be a function from x to y. Suppose a1 and a2 are two subsets of x. If a1 is a subset of a2, then the image of a1 is a subset of the image of a2. Suppose b1 and b2 are two subsets of y. If b1 is a subset of b2, then the preimage of b1 is a subset of the preimage of b2. We will prove the first statement. Suppose a1 is a subset of a2. F of a1 is the set of the images of the elements in a1, and f of a2 is the set of the images of the elements in a2. If a1 is a subset of a2, then it is easy to see that the image of a1 is a subset of the image of a2. Now we have proved that if a1 is a subset of a2, then the image of a1 is a subset of the image of a2. Similarly, we can prove that if b1 is a subset of b2, then the preimage of b1 is a subset of the preimage of b2. This completes the proof. Next, theorem 3. Suppose I is an identifier set. A sub I is a subset of x for all I. Then the image of the union of ai equals the union of the images, and the image of the intersection of ai is a subset of the intersection of the images. In short, the image of the union equals the union of the images, and the image of the intersection is a subset of the intersection of the images. First, we will prove the first identity by showing that one side is a subset of the other side. Suppose y is in the image of the union of ai. Then there exists x0 in the union of ai, such that f of x0 equals y. By the definition of union of crisp sets, there exists I0 such that x0 is in a sub I0, and f of x0 equals y. So y is in the image of a sub I0. Again, by the definition of union of crisp sets, we have y is in the union of the images. Hence, we have proved that the image of the union is a subset of the union of the images. Next, we will prove that the union of the images is a subset of the image of the union. And we will prove it in a slightly different way. We will record the relationship between upper bound and the least upper bound. It is easy to see that A sub I is a subset of the union. By theorem 2, the image of AI is a subset of the image of the union for all I. In other words, the image of the union is an upper bound of these images. The supremum, which is the least upper bound, is a subset of the upper bound. So the supremum of these images is a subset of the image of the union. What is the supremum of these images? The union. So the union of the images is a subset of the image of the union. Now we have proved that the image of the union is a subset of the union of the images. And the union of the images is a subset of the image of the union. So the image of the union equals the union of the image. Next, we will prove that the image of the intersection is a subset of the intersection of the images. Again, recall the relationship between the lower bound and the greatest lower bound. It is easy to see that the intersection is a subset of AI for all I. Again, by theorem 2, the image of the intersection is a subset of the image of AI for all I. In other words, the image of the intersection is a lower bound of these images. The lower bound is a subset of the greatest lower bound, which is the infimum. So the image of the intersection is a subset of the infimum of these images. What is the infimum of these images? The intersection. So the image of the intersection is a subset of the intersection of these images. This completes the proof. Next, theorem 4. Suppose I is an identifier set. B sub I is a subset in Y for all I. Then the preimage of the union of BI equals the union of the preimages. And the preimage of the intersection of BI equals the intersection of the preimages. In short, the preimage of the union equals the union of the preimages. And the preimage of the intersection equals the intersection of the preimages. Suppose X is in the preimage of the union of BI. Then f of x is in the union of BI. That is, there exists I0 such that f of x is in B sub I0. That is, x is in the preimage of B sub I0. Therefore, x is in the union of the preimages. On the other hand, if x is in the union of the preimages, then there exists I0 such that x is in the preimage of B sub I0. That is, f of x is in B sub I0. So f of x is in the union of BI. That is, x is in the preimage of the union. Now we have proved that the preimage of the union equals the union of the preimages. Similarly, we can prove that the preimage of the intersection equals the intersection of the preimages. This completes the proof. Next, theorem 5. Suppose B is a subset in Y, then the preimage of the complement of set B is the complement of the preimage of B. In short, the preimage of the complement is the complement of the preimage. We will prove this identity by showing that one side is a subset of the other side. On the one hand, suppose x is in the preimage of the complement of B, so f of x is in the complement of B. That is, f of x is not in B. In other words, x is not in the preimage of B. So, x is in the complement of the preimage of B. On the other hand, suppose x is in the complement of the preimage of B. That is, x is not in the preimage of B. In other words, f of x is not in B. That is, f of x is in the complement of B. So, x is in the preimage of the complement of B. Thus, we have proved that the preimage of the complement equals the complement of the preimage. This completes the proof. Next, Theorem 6. Suppose A is a subset of X. Then A is a subset of the preimage of the image of A. And if X is injective, then A equals the preimage of the image of A. Suppose X is in A. If X is an element of A, then its image f of X is an element of the image of set A. So, X is an element of the preimage of the image of A. Therefore, A is a subset of the preimage of the image of A. Now suppose f is injective. If X is an element of the preimage of the image of A, then f of X is an element of the image of A. Then there exists x0 in A such that f of x0 equals f of X. Because f is injective, we have x0 equals X, so X is in A. Now we have proved that if f is injective, then the preimage of the image of A is a subset of A. Therefore, if f is injective, then A equals the preimage of the image of A. This completes the proof. Similarly, we can prove the next theorem. Theorem 7. Let B be a subset of Y. Then the image of the preimage of B is a subset of B. If F is surjective, then the image of the preimage of B equals B. In this lecture, we have talked about the properties of the true set-valued functions induced by the classical extension principle. Next time, we will talk about the properties of the true fuzzy set-valued functions induced by the fuzzy extension principle. Thank you.